In this video we'll be looking at sequence fundamentals, arithmetic and geometric sequence fundamentals. So this unit will be on sequence and series, so this is where we're starting. And a sequence is simply just a list of numbers that follow some rule. And if you have a finite sequence, that's when the domain, so the numbers you're inputting into that rule, are set. There's a limit on them. There's a specific set of numbers that you are specifying for the domain. And an infinite sequence is one in which the domain is all positive integers. So those are the two main categories here, finite and infinite. And let's look at an example here. So in examples 1 through 3, it says list the first 4 terms of the sequence using the given function rule for the sequence. So our sequence is a sub n is equal to 3 times the quantity n minus 2. So we're going to do the first 4 terms. So we're going to do a sub 1, a sub 2, a sub 3, and a sub 4. So a sub 1 is equal to 3 times 1 subtract 2. So we're just plugging in 1 for n there. And that's going to give us 3 times negative 1, so negative 3. And then a sub 2 is going to be 3 times the quantity 2 minus 2, which gives us 3 times 0, which is 0. And the next one, 3 times the quantity 3 minus 2, so that's 3 times 1, so that's 3. Next, 3 times the quantity 4 minus 2, so that's 3 times 2, which gives us 6. So the first 4 terms of this sequence would be negative 3, 0, 3, and 6. Example 2, a sub n equals, here's our rule, so first 4 terms, a sub 1 is equal to negative 1 raised to the first power times the quantity 1 squared plus 1. So that gives us negative 1 to the first would be negative, an implied negative 1 there, and then 1 squared plus 1 would be 2, so that's negative 2. A sub 2 here equals negative 1 raised to the second power. When you raise a negative number to an even power, the result will be positive. And then we'll have 2 squared plus 1. So that's going to be a positive 3. Positive 5. 2 squared is 4 plus 1 is 5. And it's positive because this became positive when we squared that negative 1. A sub 3 is going to be equal to negative 1 to the third power, so this will result in a negative here because we're raising it to an odd power. And then this would be 3 squared plus 1, so it'll be negative. 3 squared is 9 plus 1 is 10. A sub 4, we have negative 1 to the fourth power. You raise a negative number to an even power, the result is positive. And then we would have 4 squared plus 1. 4 squared is 16 plus 1 is 17. And it is positive because this negative 1 was raised to the fourth power. Quick note, it says, notice in example 2 above that it produces an alternating sequence. This is when the successive terms, so one term after another, alternate between plus and minus. And that is the mechanism that causes that. So we discussed that here. So we were negative here. The next one was positive, then negative, then positive, and so on. That would alternate. And this is what was causing that alternating sign. Alright, example 3 here. So we have this rule. So we'll get the first 4 terms. So b sub 1 would be equal to negative 1 times root 5 raised to the first power. So that would just be negative root 5. B sub 2 is equal to negative 1 root 5 raised to the second power. So that squaring this negative is going to make it positive. If you square the square root of 5, you would just get 5. So that's positive 5. B sub 3, negative 1 root 5 to the third power. So that's going to cause that to be negative. And then, so I'm going to do it this way. So it would be negative root 5 to the third power. Then we would have raising to the square root is the same thing as raising to the 1/2 power. So we would have this negative 5 to the 1/2 all raised to the third power. So that would give us negative 5 to the 3/2 power. So we, outside to inside, we multiply these exponents. So negative 5 to the 3/2 power. Next one, b to the 4th, b sub 4, I should say, not b to the 4th, b sub 4. Negative 1 root 5 to the 4th power. So that, raising that to an even power is going to cancel out that negative. So then we just have root 5 to the 4th power. So that would be root 5, let's do it this way, 5 to the 4/2 power. So raising, this would be raising to the 1/2 power, and then you raise that to the 4th power, you get 4/2. And then that would just reduce to 5 squared, which is 25. So there are the first 4 terms, and notice we have an alternating sequence here with the numbers. Each successive term is the opposite sign of the prior one. So negative, positive, negative, positive. What is the function rule that produces this sequence? So we have a negative 1, a 1, a negative 1, a 1. So it's alternating, and it's just 1. So that's going to be that rule that we discussed a little earlier that would cause that to occur. So we raise a negative 1 to the nth power. So if you raise it to the first power, it'll be negative. You raise it to the second power, it just flips the sign. You raise it to the third power, still negative. To the 4th power, flips the sign. So every even, raising it to an even power flips it to a positive 1. Raising it to an odd power flips it, or keeps it a negative 1. All right, let's look at the next example. Okay, example 5 here. What is the function rule that produces this sequence? So we have 1, 1/2, 1/3, 1/4, 1/5. So we look for a pattern here, and we notice we could rewrite this as 1 over 1. Well, we notice the denominator is increasing by 1 each time. The denominator is 2, then 3, then 4, then 5. So this is the first term, then the second term, then the third term. So whatever term it is determines the denominator here. So our rule is a sub n is going to be equal to 1 divided by n. So if we take the third term, we get 1/3. We take the fourth term, we get 1 over 4. We take the fifth term, we get 1 over 5. So whatever term number we're taking here is going in the denominator. So a sub n equals 1 over n is the rule. All right, some notes here. A sequence in which each successive term, so that means one after the other, is the previous term plus a constant, that's arithmetic. So if we're adding each time, that's arithmetic. If we are multiplying each time, that's what they're talking about here, then that is going to be a geometric sequence. So an arithmetic sequence, we're adding each time. That constant adder is the common difference. It's called the common difference, and we usually use a variable of d for that. And you can find it by subtracting any two adjacent terms. So you just take one term, subtract it by the one before it, and that'll give you the common difference. With the geometric sequence, our common ratio is what it's called. That's the number that we're multiplying each time, and we can find that by finding the ratio of any two adjacent terms. In other words, take one term and divide it by the one before it, and that will give us the common ratio, which is the multiplier that is causing each successive value. Okay, so some examples here of the different types. It says, in the following examples, determine if the sequence is arithmetic, geometric, or neither. If arithmetic, give the common difference, that's what this stands for, and the next term of the sequence. If geometric, give r, common ratio, and the next term of the sequence. All right, so we have 5, 7, 9, 11, 13, so we're looking for a pattern. It's increasing by 2 each time. It's just increasing by 2. So that means that it's arithmetic. We're adding each time, and it continues throughout the full pattern they gave us. So the next term would be 1, 2, 3, 4, 5, a sub 6, and that would be 2 more than 13, so 15. So the common difference there, we're increasing by 2 each time, would be 2. Okay, next one, we have 1, then 3, then 9, then 27. So here we're multiplying by 3. 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27. So we have a common ratio of 3. We're multiplying by 3, so this is a geometric sequence. Geometric. And the next one would be 27 times 3, which would be 81, and that would be 1, 2, 3, 4, the fifth term. So we'll say that's a sub 5. All right, next one, example 8. We have 1/2, 1/3, 1/4, 1/5. So it doesn't appear we're adding anything, and we're not multiplying either. So this one is going to be a neither. It's neither arithmetic or geometric. So let's see if we can find the rule. Sometimes it's good to put the term numbers. So this is the first term, the second term, the third term, the fourth term. So I notice that the denominator is going up by 1 each time. And I also notice that the denominator is 1 bigger than the sequence number here. So this is the second term. I should say term number, not sequence number. So that's the second term, but its denominator is 3. This is the third term. Denominator is 1 more than that, 4. This is the fourth term. Denominator is 1 more than that, 5. So the rule for that is 1 over n plus 1. So let's check it. If n is 1, that would be 1/2. Check. If n is 2, that would be 2 plus 1, or 3 in the denominator. Check. If the n value is 3, that would be 3 plus 1, or 4 in the denominator. Check. If n is 4, that would be 4 plus 1, or 5 in the denominator. Check. So this is the appropriate rule, but it is neither arithmetic or geometric. That's it for this video.